Okay, so this is Chapter 13, Equilibrium. This unit is going to be divided into 3 lessons. You will probably have to watch the first 2 lessons in order to get through the first problem set in Chapter 13. So the first 2 lessons are going to focus on what is equilibrium, the equilibrium constant, equilibrium and pressure, and calculations involving equilibrium. And the last one will include some advanced calculations involving equilibrium and Le Chatelier's principle. So what is equilibrium? Let's use an analogy. If you go to a dance, who is present at the dance? Now, you might say, students, boys, girls, teachers, safety staff, custodial people. However, if we just say boys and girls, then we can cover everyone that's at the dance. So what usually happens is that sometimes boys and girls make couples. And couples can also break up. And you have boys and girls. So in this very generic sense, this represents an equilibrium relationship. So what happens at a high school dance? Well, you might have the number of boys that are at the dance look something like this, increases, and then it levels off. The girls, maybe there's a little bit less girls at the dance than boys, so it might look like this. And then you may have some couples, or maybe some boys and girls form couples while they're at the dance, and that looks like this. During this section right here, we have equilibrium. So what happens is, as time goes on, you have B plus G yielding C. So basically, we have B plus G yields C. And we have the purpose of this double arrow, which is that the reaction is reversible. So as boys and girls become couples, couples can break down and become boys and girls again. So that's equilibrium in a very generic sense. So let's apply it to chemistry. So chemical equilibrium is the condition in which the concentration of all reactants and products in a closed system cease to change with time, and that's because the system is closed. This occurs when opposing reactions are proceeding with equal rates. So at equilibrium, rates are equal. So we're talking about the rate of the forward reaction is equal to the rate of the reverse reaction. The reactants and the products cease to change with time at equilibrium. So at equilibrium, the products and reactants are constant. And that you actually learned in Regents Chem. It requires a closed system. So what we can say is if we have H2 gas and O2 gas forming H2, the rate at which hydrogen and oxygen are combining to form water is equal to the rate at which water is breaking down again to form oxygen and hydrogen in a closed system. And again, the double arrow is used to indicate the reversible reaction. Rate constants are given for various reactions to determine when a system is at equilibrium. So here we're using a generic species A that's in the gas state changes into species B in the gas state. It's a reversible reaction. So if we were to write a rate, we would say rate equals Kf. So this is the constant of the forward reaction times the concentration of species A. For the reverse reaction, it would be rate equals the constant for the reverse reaction for species B. Now, I just want to review this. You should know this. If you don't remember it, you might want to jot it down somewhere. There are some added things in this lesson that aren't in your notes, so it would be useful to have some spare paper. When we're talking about equilibrium, we're going to talk about three things. We're going to talk about an equilibrium constant. We're going to talk about equilibrium and pressure, and we're going to talk about equilibrium and concentration. So for gases, remember that concentration M is proportional to the quantities determined by the gas law. So let's review. You have Pervnert, okay? And molarity equals moles over volume. So if I substitute molarity in the Pervnert equation in place of moles and volume, I get M equals P divided by RT. All I did was substitute the M in here, and solving for molarity, I get P divided by RT. Now, molarity is concentration, which in this case could be species A. So now I have the concentration of species A, because concentration is molarity, moles per liter. So this is really the molarity of species A is equal to the pressure of A over RT. And if I had a B, concentration of B is equal to the pressure of B over RT. So going back to my rate, in which I said on the previous page, I said that rate of the forward was equal to Kf of the concentration of species A. I just said that A equaled PA over RT, so I can substitute that in here, which is what I did. Okay, I substituted in PA right there over RT. And then my other equation was rate equals KR of species B. And all I did was substitute this in for the concentration of B. At equilibrium, the rates are equal to each other. So at equilibrium, rates are equal. I just told you this on the previous page. And here you can see that the reactants PA, PB are constant. So this is products and reactants. Okay, definition of equilibrium. Well, I just told you. Let's sum it up now. rate of the forward reaction is equal to the rate of the reverse reaction. And I also told you that the concentration of products and reactants are constant. Okay. Equilibrium is dynamic. And what we mean by that is that changes, and they're really small changes in response to stress. So the dynamic part means that it's constantly changing. It is not static, but the changes are so small, okay, it's considered equilibrium. So, for example, you don't have to draw this, but if I had a closed container, here's a jar, and I had water in here, and this is H2O liquid. I also have H2O gas up here. The rate at which the liquid is turning into a vapor and the vapor is turning into a liquid is equal. If I open the container, of course, then I'm not going to have any equilibrium because all the water will evaporate. So that's really important when we said that it has to be in a closed system. Okay, the equilibrium constant is a proportion of products to reactants. And this law of mass action that we use to determine the equilibrium constant was actually discovered by some Norwegian chemists, Gullberg and Weig. Now I want you to realize that in this generic equation, A, B, C, and D are species, so chemical formulas, and J, K, N, and M are coefficients. So that's your general reaction, okay? Now, remember, as I said, Kc, so that we're talking about the equilibrium constant, and we're talking about this in relation to concentration, is going to be the products over the reactants. And I'm just going to circle this and put concentration. I mean, I know what it is because we're also going to talk about one for pressure. So products over reactants, that means I'm going to have the concentration of C raised to the nth power times the concentration of D raised to the mth power divided by the concentration of A to the J power times the concentration of B to the K power. So just to give you an example with something concrete, let's use an example of N2 gas plus 3H2 gas yields 2NH3 gas. And if I asked you to set that up and write an equilibrium expression for what was happening in this reaction, you would write Kc equals, remember it's products over reactants, so I've got the concentration of NH3 to the second power, because the coefficients are our exponents, over the concentration of N2, no exponent, times the concentration of H2 to the third power. Now this value of Kc is constant, hence the name constant, at a specified temperature. If you change the temperature, you're going to change the constant, which is important to remember. So let's review. Keq is the equilibrium constant. Kp, as you are going to see, is used for gases, for pressure, and Kc is used for solutions concentrations. It expresses the ratio of the product molarities to the reactant molarities at equilibrium raised to the corresponding powers of the number of moles of a substance. When we say number of moles of a substance, we're talking about coefficients. So all that did was review what I just told you. And here they're using C, D, A, B. Same thing. Okay. Let's talk about the meaning of K. We're not going to ponder it quite as in depth as the meaning of life, but it will get pretty in depth. Keq, using this example, we have H2 plus I2 yields 2HI, so our equilibrium expression is HI squared, because this has got a 2 in front of it, over concentration of H2 times the concentration of I2. Now, when we solve for the equilibrium constant, if Keq is greater than 1, that means that the product is favored. Because obviously if the concentration of HI is greater than the concentration of H2 and I2, then K will be greater than 1. If K is less than 1, that means that the reactants are favored. When K is much greater than 1, then the equilibrium lies to the right, okay, meaning product side. And when the equilibrium equilibrium constant is much less than 1, then the equilibrium lies to the left. The equilibrium constant expression for a reaction written in one direction is simply the reciprocal of the reverse reaction. Many reactions are easy to measure using partial pressures. So some of the problems you see are going to be with Kc, concentration, and some of them are going to be with Kp for pressure. So for this reaction, okay, and here Kp equals pressure, if we were to set this up, well, let me show you what the original, if I were using the original setup, or the original equation that I used as an example, where I had C to the nth, D to the mth over A to the J, and B to the K at the top of the page. Okay, if I did that for pressure, it would look like this, Kp, because it's pressure. So now it's the pressure of C raised to the nth times the pressure of D raised to the mth over the pressure of A to the J times the pressure of B to the K. In using the example right here of nitrogen gas and hydrogen gas forming ammonia, it would be the pressure of NH3 to the second over the pressure of N2 and the pressure of H2 to the third. So what is the relationship between Kc and Kp? Well, Kp equals Kc times RT raised to the delta N, where delta N is equal to the change in the number of moles of gas. Delta N is equal Okay, so let me just give you a very basic generic so you can see how this looks like. Let's just suppose Kc is equal to 21.3 at 300 Kelvin. And I wanted you to find Kp. So Kp is equal to 21.3 times R is 0.0821 times 300, okay? And that's going to be change in N. So let's go up here to the top. We have 1 plus 3, and we have 2. So this is going to be change the number of moles of gas. I left out one thing. Products minus reactants. So in this case, in our example, it's going to be 2 minus 4, which is -2. So this is going to be raised to the -2. So when I solve for this, I get a Kp equal to 0.035. Okay, and there are no units for K. So this is like the one time that you can get away without writing units. Because it's a constant, there are no units. Okay, so let's just do a few of these. Write the equilibrium expressions for each of the following. So for A, this is a gas, so this would be Kp is going to be equal to the concentration of the pressure of SO3 squared over the concentration of the pressure of O2 times the concentration of the pressure of SO2 squared. So this is for number 1. Let's do number 2 over here. So we've got Kp is equal to, we have NO2, so we've got the pressure of NO2 times the pressure of O2 over the pressure of NO and the pressure of O3. And for the third one, we've got Kp is equal to the pressure of O2 to the third divided by the pressure of O3 to the second. And the last one, Kp is equal to the pressure of SO3 to the second divided by the pressure of O2 times the pressure of SO2 to the second. So A says at 25 degrees, the pressures at equilibrium were found to be, and they gave us SO3 is 2.5 atm, pressure of O2 is 0.045 atm, and the pressure of SO2 is equal to 0.75 atm. So we're using this equation because this is referring to number 1. And so now we're going to substitute in Kp is equal to, we need SO3. SO3 they said was 2.5, so 2.5 squared divided by O2, which is 0.045, times SO2, which is 0.75, and that is squared. And you get 246.9. And that is our Kp. Next one, using the Kp from the above equation, calculate the value of Kc at 25 degrees Celsius. So we said get Kp equals Kc times RT to the delta N. Our Kp is 246.9 equal to Kc times our R, 0.0821. We said 25 degrees Celsius. We need that in Kelvin, which is going to be 298. And that's raised to, let's look at our gas. We have 2 minus 3 is -1. So then we solve for Kc. And I got a Kc equal to 6040.6. Reverse reactions. Here you have a reaction, so your KEQ would be pressure of NO2 squared divided by the pressure of N2O4 equals 6.46. When you reverse the reaction, you get PN2O4 over PNO2 squared equal to 0.155. So here's some tricks. The KEQ of a reaction in the reverse reaction is the inverse of the KEQ in the forward reaction. So let's go back for a second. So if you take the inverse of this, you get 1 over 6.46, which is going to equal 0.155, which is what we got right here. So that's a really neat trick. The KEQ of a reaction that has been multiplied by a number will be equal to the KEQ raised to the power of that number. And the KEQ for a net reaction made up of 2 or more steps is the product of the equilibrium constants of the individual steps. So those are some tricks and shortcuts that you'll see as we go through some problems and you do the problem set. Couple more tips and tricks. When substances in a reaction are all in the same phase, we refer to the system as a homogeneous equilibria. Different phases is a heterogeneous equilibria. For example, you have PbCl2 solid yielding Pb2 plus aqueous and 2Cl aqueous. So is it true that our equilibrium expression would be the concentration of Pb times the concentration of Cl minus raised to the second over the concentration of PbCl2? Is that true? It is not. This is extremely important. Pure solids and pure liquids are not included in the expression because they have a reference concentration equal to 1. We do not have a specific number of moles dissolved in a certain volume. So the corrected equation would simply just be the concentration of Pb ions times the concentration of chlorine ions raised to the second power. So extremely important. Whenever you see a solid or a liquid in an equation, it is not part of the equilibrium expression. So let's do a summary before we get started in some problem solving. Partial pressures of gases are used in the expression. Molar concentration of dissolved species are used in the expression. Pure solids and liquids are not used in the expression. And to determine KEQ, you must utilize conditions at equilibrium, which only varies by temperature and nothing else. Okay, the reaction quotient, Q. The result when reactant and product partial pressures or concentrations are substituted into a KEQ expression. So often you'll be given information in a problem and you're really solving it for Q, the reaction quotient, and then you're comparing that to a known KEQ. So when you calculate if your Q is equal to your KEQ, then that system is at equilibrium. If your Q is greater than your KEQ, then the forward reaction predominates. And what will happen is it'll shift back to the reactants to reach equilibrium. So if your Q is greater than your KEQ, that means we're driving the forward reaction, and the reverse reaction is going to kick in to reach equilibrium again. If your Q is less than your KEQ, that means that the reverse reaction predominates, and what will happen is we will shift toward the products, meaning we're going to drive the forward reaction to reach equilibrium. Q is used to determine how concentration or pressures need to be adjusted to reach equilibrium. That's really the basis of what Q is. Okay, so somehow the calculations involving equilibrium, the directions, they must come after this. So how to solve for equilibrium problems? First of all, you must start with a balanced equation. So if we inspect here, we can see that this is definitely balanced. You're going to write down the amounts, either concentration or pressure units, in an ICE table, sometimes called a rice table. I'll explain that. And then shift the equilibrium by subtracting and adding x to either side of the equation. Solve for x using your solver in your calculator. I can show you how to do that. Or you can do it by hand if you wish to torture yourself. And sometimes the equations must be solved in reverse. So, for which of the following situations is the system at equilibrium? For those which are not at equilibrium, in which direction will they shift? So I'm going to do, on the next couple of slides, you're going to write this down on your page and notes, and I have a slide for A, B, and C. So for part A, we write the expression. We've got HOCl squared over H2O times Cl2O. And they give us 0.09. So the 0.09 is at 25 degrees. They gave us in the problem. And we're going to compare the reaction quotient, that's what you're solving for the given conditions. They told us that the concentration of HOCl was 21 torr squared over the concentration of H2O, which is 200, times the concentration of Cl2O, which is 49.8. That gives us a 0.044. So you're comparing 0.044 and 0.09. Well, you can see that this is less. So Q, this is my Q, is less than K. When Q is less than K, the ratio of the initial reactants is greater than the products, so it is going to shift right. When my Q is less than my K, that means the ratio of my reactants is greater than my products, so it's going to shift right to try to use up some of those reactants and reach equilibrium. In the next one, in B, they told us that each of the initial concentrations were 1. So when we compare this, our Q is equal to 1 and our K is equal to 0.09. So our 1 is greater than our K. What that means is that the products are greater, the initial concentration of our products are greater than our reactants, so this is going to shift left. It's going to shift left to try to use up some of the products to reach equilibrium. And in our last one, they told us that HOCl is 20 torr, that's squared. Water was 296 torr, and Cl2O was 15 torr. So here we have Q and K, and they are equal. K is equal to Q, so I am at equilibrium, no shift occurs. More strategies. If a problem gives both the initial and the equilibrium concentrations of a species, then determine the change and apply it stoichiometrically to other species. If all equilibrium conditions are not given, then use algebra to predict what they should be in an ideal situation. Quadratic equations may have to be used to solve for x if there's a significant change in values at equilibrium. Use equilibrium values only to calculate K. Okay. Those were the directions that I already read to you. We are now going to solve a problem, and I'm going to show you how to solve for x using the solver in your calculator. So in this example, the value of the equilibrium constant for the following reaction is 1.5 times 10 to the negative fifth. So this is my K. I have a balanced reaction, 2H, 2H, 2F, 2F. I have an initial concentration of 2.0 molar. What are the final concentrations of all species once equilibrium is established? Again, I'm going to show you on a slide. You're going to write the information down in this section. This is called a RICE or ICE table. RICE stands for reaction, initial change equilibrium. Most teachers, as I do myself, refer to it as simply an ICE table because you always have your reaction written at the top. Then you have your I for initial, your C for change, your E for equilibrium. Now they told us that the initial concentration of HF was 2 molar. So I'm going to write that down in the initial column. At the start of the reaction, my H2 and my F2 are 0. As the reaction proceeds, HF is used up. So it's going to be minus 2x. Now, this 2 is here because of this 2, the coefficient. So as the reaction proceeds, some concentration, some amount, x, is going to be used up. But HF is used up at twice the rate at which H2 and F2 are formed. So it becomes minus 2x. On this side, x is going to appear because we're forming H2 and F2. So at equilibrium, equilibrium is my initial, the difference between my initial and my change. So 2 initial minus 2x, and this is simply x. If I were to write an equilibrium expression, I would have concentration of H2 times F2 over HF squared because of the coefficient of 2. So that's my ICE table. Now I'm going to substitute in. So I just said H2 times F2 over HF squared. We were given this in the problem. That is our K. Now I substitute in, this is my equilibrium concentrations. I had x times x divided by 2 minus 2x, and that was squared because of the coefficient equaling this. If I set this up as an equation, I'm going to multiply both sides by 2 minus 2x squared. These cancel. So now I'm left with this equaling x squared. Now we're going to use the solver feature on the graphing calculator. Now if I wanted to put this into an equation of a line, in the form of an equation, I would have 0 equals 1.5 times 10 to the minus 5th times 2 minus 2x squared minus x squared equals 0. I don't think I have to teach basic algebra. At least I hope not. Okay. Let's use the solver. So on your calculator you click Math and then choose 0 for equation solver. Hit clear if necessary in case you have something in there. You're going to rewrite the equation, set it equal to 0, which is what I just showed you. You're going to type the equation into the solver using the X button right next to alpha. Once you have the equation typed in, you hit enter. Then you type in a guess for X. You can't have a negative concentration, so the rule of thumb is that you choose about 1% of the initial concentration. So if the initial concentration was 2 molar, then 10% of that is about 0.02. So you put 0.02 in for X, and then you're going to hit alpha solve, and then you will get a value for X. Once you do that, so basically, okay, so I did this, I got a value for x. So my value for x was 0.007. Now remember, x is equal to the concentration of H2. It's also equal to the concentration of F2. So that is equal to 0.007 molar. Now, if you hit quit out of the solver, and then just simply type 2 minus 2x, the calculator remembers what the value for x is, and it will tell you 1.98. That is our value for HF. Now you could also use the small x assumption rule, which is explained in the textbook, and I will explain it a little bit later on in the lesson. All right. The value of the equilibrium constant for the following reaction at 500 K is 4.35. So here's our K value. Here's our reaction. Now notice this is not balanced. This needs to have a 3 here. If the initial concentration of N2 is 2.3 and the initial concentration of H2 is 1.25, what is the total of the concentrations of all species once equilibrium is established? Small x assumption won't work here because the K is too big. You can only use small x assumption when the K is extremely small. We have to use the solver. But now you're going to guess somewhere around 1 for x, and then alpha solve. So let's look at how this is done. Here's our equation. This should say 3H2, 2NH3. Did this one have the 2? Yeah. Okay. So our initial concentration of N2 was 2.3. Our initial concentration of H2 was 1.25. At the start of the reaction, there is no concentration for NH3. So as the reaction proceeds, N2 disappears, minus x. H2 disappears at minus 3x because of the coefficient. And NH3 appears as 2x. At equilibrium, it's 2.3 minus x, 1.25 minus 3x, and 2x. Our equation is K is equal to 4.35. We have NH3 product squared over the concentration of N2 times the concentration of H3 cubed. Substituting in our values, K equals 4.35 equals 2x squared, because of that, over 2.3 minus x times 1.25, 3x cubed. When we set this equal to 0, we get 4.35 times 2.3 minus x times 1.25 minus 3x cubed minus 4x squared, because 2x squared is 4x squared. So I go to math 0, which is my solver. I clear it out. I type in this equation. Then once I type in the equation, I hit enter. And remember, we said that we were going to enter a 1 for our initial concentration, and then we're going to hit alpha solve. And we get x equal to 0.301. Now we can hit quit. Once we see what x is, we jot it down. We can hit quit. Then we can type in 2x equals, and it's going to tell us 0.6 molar, which is equal to the concentration of NH3. Then we can type in 1.25 minus 3x, and it will hit enter, and it'll tell us 0.35 molar, which is H2. And then we can actually type in 2.3 minus x, and that will tell us 1.99, which is approximately 2 molar for N2. Okay. I think I'm going to stop here for tonight and save the rest of it for the second half. There's going to be 2 more videos, but the second video will also be more problem solving with equilibrium.